Chapter 6, Empirical Model Identification. To this point, we have been modeling processes using fundamental principles, and this approach has been very valuable in establishing relationships between parameters in physical systems and the transient behavior of the systems. Unfortunately, this approach has limitations which generally result from complexity of fundamental models. For example, a fundamental model of a distillation column with 10 components and 50 trays would have on the order of 500 differential equations. In addition, the model would contain many parameters to characterize the thermodynamic relationships, K equilibrium values, rate processes, heat transfer coefficients, and modeling non-idealities, tray inefficiencies. Therefore, modeling most realistic processes requires a large engineering effort to formulate the equations, determine all parameters, values, and solve the equations usually through numerical methods. This effort is justified when very accurate predictions of dynamic responses over a wide range of process operation conditions are needed. This chapter presents a very efficient alternative modeling method specifically designed for process control, termed empirical identification. The models developed using this method provide the dynamic relationship between selected input and output variables. For example, the empirical model for the distillation column discussed previously could relate the reflux flow rate to the distillate composition. In comparison to this simple empirical model, the fundamental model provides information on how all of the tray and product compositions and temperatures depend on variables such as reflux. Thus, the empirical model described in this chapter, while tailored to the specific needs of control processing, does not provide enough information to satisfy all process design and analysis requirements and cannot replace fundamental models for all applications. In empirical model building, models are determined by making small changes in the input variables with a nominal operating condition. The resulting dynamic response is used to determine the model. This general procedure is essentially an experimental linearization of the process that is valid for some region about the nominal conditions. As we shall see in later chapters, linear transfer function models developed using empirical models are adequate for many process control designs and implementations. Because the analysis methods are not presented until later chapters, we cannot yet definitely evaluate the usefulness of the models, although we will see that they are quite useful. Thus, it is important to monitor the expected accuracy of the modeling methods in this chapter so that it can be considered in later chapters. So it's important to monitor the expected accuracy of the modeling methods. Next, as a rough guideline, the model parameters should be determined within 20%, although much greater accuracy is required for a few multivariable control calculations. The empirical models involve designed experiments during which the process is perpetuated to determine dynamic data. Perpetuated or perturbated, the success of the method requires close adherence to principles of experimental design and model fitting, which are presented in the next section. In subsequent sections, two identification methods are presented. The first method is termed the process reaction curve and employs simple graphical procedures for modeling fitting. The second and more general method employs statistical principles for determining the parameters. Several experiments are presented with each method. The final section reviews some advanced issues and other methods are not presented in this chapter so that the reader will be able to select the most appropriate technology for model building. 6.2, an empirical model building procedure. Empirical model building should be undertaken using the 6-step procedure shown in figure 6.1, starting with the experimental design, then the planned experiment, then the determined model structure, then the parameter evaluation, then the diagnosis evaluation, then the model verification. And this procedure ensures that proper data is generated through careful experiment design and execution. Also, the procedure makes the best use of the data by thoroughly diagnosing and varying results from the initial model parameter calculations. The schematic in figure 6.1 highlights the fact that some a priori knowledge is required to plan the experiment and that the procedure can and often does require iteration, as shown by the dashed lines. At the completion of the procedure described in this section, an adequate model has been determined, or the engineer will be at least know the satisfactory model. Should I mess that up? At the completion of the procedure described in this section, an adequate model should be described, or the engineer will at least know that a satisfactory model has not been identified and that further experimentation is required. Through this chapter, several experiments and examples are presented. The first example is shown in 6.2. Figure 6.2 shows example process for empirical model identification. This is a CSTR in series, so 2 CSTRs. The process model to these identified relates the valve opening to the heating oil line and the outlet temperature of the second tank. I might have said CSTRs, but you can just refer to them as stirred tank reactors. It's a more acceptable form for all cases. The experimental design. An important and often underestimated aspect of empirical modeling is the need for proper experimental design. Since every method requires some type of input perturbation, the design determines its shape and duration. It also determines the base operating conditions for the process, which essentially determine the conditions about which the process model is accurate. Finally, the magnitude of the input perturbation is determined. This magnitude must be small enough to ensure that the key safety and product quality limitations are observed. It's important to begin with a perturbation that is on the small, safe side rather than cause a severe process disturbance. Clearly, the design requires a purporting information about the process and its dynamic responses. This information is normally available from previous operating experience. If no prior information is available, some preliminary experiments must be performed. For the example in figure 6.2, the time constants for each tank could be used to determine the first estimate of the response of the entire system. A result of this step is the complete plan for the test, which should include 1 through 4, a description of the base operating conditions, a definition of the perturbation, a definition of the variables to be measured, along with the measurement frequency, and an estimate of the duration of the experiment. Naturally, the plan should be reviewed with all operating personnel to ensure that it does not interfere with other planned activities. Next, the plant experiment. The experiment should be executed as close to the plan as possible. While variation in plant operation is inevitable, large disturbances during the experiment can invalidate the results. Therefore, plant operation should be monitored during the experiment. Since the experiment is designed to establish the relationship between one input and output, changes in other inputs during the experiment can make the data unusable for identifying a dynamic model. The monitoring must be performed throughout the experiment using measuring devices when available and using other sources of information such as laboratory analysis when processes and sensors are not available. This monitoring process must be performed throughout the experiment using measuring devices where available and using other sources of information such as laboratory analysis when process sensors are not available. For the example in figure 6.2, variables such as the feed inlet temperature. Variables such as the feed inlet temperature affect the outlet temperature of the second tank, and they should be monitored to ensure that they are approximately constant during the experiment. Next, determining the model structure. Currently, many methods are available to calculate the parameters in a model whose structure is set. However, a few methods exist for determining the structure of a model, first or second transfer function, based solely on the data. So there are methods in which we can find a model based on the data. Typically, an engineer must assume a model structure and subsequently evaluate the assumption. The initial structure is selected based on prior knowledge of the unit operation, perhaps based on the structure of the fundamental model, and based on patterns in the experimental data just collected. The assumption is evaluated in the later diagnostic step of the procedure. The goal is not to develop a model that is exactly matching the experimental data. Rather, the goal is to develop a model that describes the input and output behavior of the process adequately for use in process control. Empirical methods typically use lower order linear models with dead time. Often, but not always, first order with dead time models are adequate for process control analysis and design. At times, higher order models are required, and advanced empirical models are available for determining the model structure. Next, parameter evaluation. At this point, a model structure has been selected and data has been collected. Two methods are presented in this chapter to determine values for the model parameters so that the model provides a good fit to the experimental data. One method uses a graphical technique, the other uses statistical principles. Both methods provide estimates for parameters in transfer function models, such as gain, time constant, and dead time. In a first order with dead time model, the methods differ in the generality allowed in the model structure and the experimental design. Next, we look at diagnosis evaluation. And just to say a note, we talked about experimental design and we talked about the plan design. We are just talking about figure 6.1. So it's a good idea just to keep figure 6.1 right here. Diagnosis evaluation. Diagnostic evaluation. Some evaluation is required before the model is used for control. The diagnostic level of evaluation determines how well the model fits the data used for the parameter estimation. Generally, the diagnostic evaluation can use two approaches. One, a comparison of the model prediction with the measured data, and two, a comparison of the results with any assumption used in the estimation model. Next, the verification. A final check on the model is to verify it by comparison with additional data not used in the parameter evaluation. Although this step is not always performed, it is worth comparing the model to data collected at another time to be sure that the typical variation in plant operation does not significantly degrade model accuracy. The methods used in this book are the same as the diagnosis evaluation step. It is appropriate to emphasize once again that the model developed by this procedure relates the input perturbation to the output response. The process model includes all equipment between the input and the output. Thus, the typical model includes the dynamics of the valves and sensors, as well as the process equipment. As we will see later, this is not a limitation. In fact, the empirical model provides the proper information for control analysis because it includes the elements in the control loop. Finally, two conflicting objectives must always be balanced in performing this experimental procedure. The first objective is the maintenance of safe, smooth, and profitable plant operation, for which a small experimental input perturbation is desired. However, the second objective is the development of an accurate model for process control design that will be improved by a relatively large input perturbation. The proper experimental procedure must balance these two objectives by allowing a short-term distance so that the future plant operation is improved through good process control. 6.3. The process reaction curve. The process reaction curve is probably the most widely used method for identifying dynamic models. It is simple to perform, and although it is the least general method, it provides adequate models for the applications. First, the model is explained and demonstrated through an example, then it is critically evaluated with strong and weak points noted. The process reaction curve method involves the following four actions. Allow the process to reach steady state. Next, introduce a single step change in the input variable. Next, collect input and output response data until the process again reaches steady state. Next, perform the graphical process reaction curve calculation. The graphical calculation determines the parameters for a first order with dead time model. The process reaction curve is restricted to this model. The form of the model is as follows, with xs denoting the input and ys denoting the output, both expressed in terms of deviation variables. Equation 6.1, I'm almost certain this is only concerning a first order process with dead time. There are two slightly different graphical techniques in common use, and both are explained in this section. The first technique, which is also termed method 1, adapted by Ziegler and Nichols, uses the graphical calculation shown in 6.3 for the stirred tank process in figure 6.2. The intermediate values determined from the graph are the magnitude of the input change, fancy D, the magnitude of the steady state change in the input, delta, and the maximum slope of the output versus time plot, S. The values from the plot can be related to the model parameters according to the following relationships for a first order with dead time model. The general model for a step in the input is t is greater than or equal to theta, and this is given by equation 6.2. We have deviation variable y with, in terms of t, equals the proportional gain times fancy d times 1 minus e to the power negative t minus theta over tau. The slope for the response at any time t greater or equal to 2 theta can be determined by equation 6.3, and this is given as a differential deviation variable y of variable t over dt, and the maximum slope occurs at t equals theta, so s is equal to delta over tau. Thus, the model parameters can be calculated as kp equals delta over fancy d, tau equals delta over s, theta equals the intercept of maximum slope with initial value, as shown in figure 6.3. A second technique, method 2, uses the graphical calculations shown in figure 6.4. The intermediate values determined from the graph are the magnitude of the input change, fancy D, the magnitude of the steady state change in the output, delta, and the times at which the output reaches 28 and 63% of its final value. The values from the plot can be related to the model parameters using the general expression in equation 6.2. Any two values of the time can be selected to determine the unknown parameters, theta and tau. Theta, remember, is the intercept of the maximum slope with initial value. Tau is the time constant. The typical times are selected where the transient response is changing rapidly so that the model parameters can be accurately determined in spite of measurement noise. The expressions are given by equation 6.5. Y of variable theta plus t equals delta times 1 minus e to the power negative t. Next we have y of variables theta plus tau over 3 equals delta times 1 minus e to the power t over 3. I've been saying t, but that's actually 1. So equation 6.4, e raised to the power of 1. Here we have figure 6.4. It's the process reaction curve. It's for method 2. Method 2 and method 1. I remember doing this in the homework. Method 1 is a more general and is a more generally accepted method. It's easier. Method 1, I've been talking about method 2, and then method 1 is still used. So that's the point I'm trying to get at. Moving on, thus the values of time at which the output reaches 28.3 and 63.2% of its final value are used to calculate the model parameters. 6.6, we have t 28% equals theta plus tau over 3, and t 63% equals theta plus tau. We have tau and theta. And those are simply, you just plug them in, it's pretty easy to use these. So ideally, both techniques should give good representation models. However, method 1 requires the engineer to find a slope, aka a derivative of a measured signal. Because of the difficulty in evaluating the slope, especially when the signal has high frequency noise, method 1 typically has larger errors in the parameter estimates, thus method 2 is preferred. Example 6.1, the reaction experiment have been performed on the stirred tank system in figure 6.2, and the data is given in figure 6.3 and 6.4 for methods 1 and method 2, respectively. Determine the parameters for the first order with dead time model. The solution is given. The graphical calculations are shown in figure 6.3 for method 1, and the calculations are summarized as follows. We have variables and values for fancy D, delta, proportional gain Kp, S, tau, and theta. The graphical results are shown in figure 6.4 for method 2, and the calculations are summarized below. Note that the calculation for Kp and delta and fancy D are the same and thus not repeated. Also, time is measured from the input step change. We have more variables than we don't have more variables, we simply employed equation 6.6 given our given data. Further details for the process reaction curve method are summarized below with respect to the 6-step empirical procedure. So again, we are talking about the experimental design, the planned experiment, the diagnosis, evaluation, the verification. And these are steps that we just talked about, but we're talking about it even further. And we need to pop up figure 6.1 again. This is procedure for empirical transfer function model identification. For experimental design, the calculation procedure is based on a perfect step change in the output as demonstrated in equation 6.2. The input can normally be changed in a step when it is manipulated variable, such as valve % open. However, some control designs will require models for inputs, such as feed composition, which cannot manipulate in a step, if at all. The sensitivity of the model results to deviations from a perfect input step as shown in figure 6.5, for an example in which the true plant has a dead time of 0.5 and a process time constant tau sub-process of 1. In addition to the input shape, the input magnitude is also important. As previously noted, the accuracy of the model depends on the magnitude of the input step change. The output change cannot be too small because of the noise in the measured output, which is caused by many small process disturbances and sensor non-idealities. The output signal is the magnitude of the change in the output variable. Naturally, the larger the input step, the more accurate the model results, but the larger the disturbance to the process. A rough guideline for the process reaction curve is that the signal-to-noise ratio should be at least 5. The noise level can be estimated as the variation experienced by the output variable when all measured inputs are constant. For example, if an output temperature varies plus or minus 1 degree Celsius due to noise, the input magnitude should be large enough to cause an output change delta of at least 5 degrees Celsius. Finally, the duration of the experiment is set by the requirement of achieving a final steady state after the input step. Thus, the experiment would be expected to at least last a time equal to the dead time plus 4 time constants, theta plus 4 times tau. In the stirred tank example, the duration of the experiment could be estimated from the time constants of the two tanks plus some time for the heat exchanger and sensor dynamics. If the data is not recorded continuously, it should be collected frequently enough that the graphical analysis, 40 or more points, would be preferable, depending on the amount of high frequency noise. Next, we're looking at plant evaluation, and remember this is just figure 6.1. Since model errors can be larger if another perhaps unmeasured input variable changes, experiments should be designed to identify whether disturbances have occurred. One way to do this is to ensure that the final condition of the manipulated input variable is the same as the initial condition, which naturally requires more than one step change. Then, if no output variable also returns to its initial condition, one can reasonably assume that no long-term disturbance has occurred, although a transient disturbance could take place and not be identified by this checking method. If the final value of the output variable is significantly different from its initial value, the entire experiment is questionable and should be repeated. Again, if the final value of the output variable is significantly different from its initial value, the entire experiment is questionable and should be repeated. This situation is discussed further in example 6.3. Next, we're looking at diagnostic evaluation. The basic technique for evaluating results of the process reaction curve is to plot the data and the model predictions on the same graph. Visual comparison. I'm just going to say this again. The basic technique for evaluating results of the process reaction curve is to plot the data and the model predictions on the same graph. Visual comparison can be used to determine whether the model provides a good fit to the data used in calculating its parameters. Visual comparison can be used to determine whether the model provides a good fit to the data used in calculating its parameters. This procedure has been applied in example 6.1 using the results from method 2, and the comparison is shown in figure 6.6. Since the data and the model do not differ by more than about 0.5 degrees Celsius throughout the transient, the model would normally be accepted for most control analysis. Most of the control analysis method presented in the later parts of the book require linear models, and information on strong nonlinearities would be a valuable result. Here we have figure 6.6, comparison of measured and predicted outputs. Next we have figure 6.7, example of experimental design to evaluate the linearity of a process.
You got a fast car. I got a plan to get us out of here, working at the convenience store. Meant to save just a little bit of money. Won't have to drive too far. Just cross the border into the city.
Next, we have the verification. If additional data is collected that is not used to calculate the model parameters, it can be compared with the model using the same technique as in the diagnostic step. We have example 6.2, a more realistic set of data for the two stirred tank heating process is given in figure 6.8. This data has noise, which could be due to imperfect mixing, sensor noise, and variation of other input variables. The application of the process reaction curve requires some judgment, and the reader should perform both methods on the data and note the difficulty in method 1. Typical results for the methods are given in the following table, but the reader can expect to obtain slightly different values due to the noise. We have method 1 and method 2. We have proportional gain constants, we have theta, and we have tau. Remember, theta was like that maximum curve with respect or something with the initial value. Maybe it's the steady value, maybe it's the initial. Let's go back and check what that theta is. Theta is the intercept of maximum slope with initial value. Theta initial value. We have figure 6.8, the process reaction curve for example 6.2, and we have figure 6.9, experiment data for process reaction curve when input is returned to its initial condition. Example 6.3, data for two step changes is given in figure 6.9. Determine a dynamic model using the process reaction curve method. Note that there is no difference between the initial and final values of the input valve opening. However, the output temperature does not return to its initial value. And this is due to some non-ideality in the experiment, such as unmeasured disturbances or a sticky valve that did not move as expected. Naturally, the output variable will not return to exactly the same value, but the difference between the initial and final values in the example seems suspiciously large, because 4 degrees Celsius is 50% of the temperature change occurring during the experiment. Therefore, this data should not be used and the experiment should be repeated. We will move on to example 6.4. A fundamental model for a tank mixing process similar to figure 6.10a will be developed in chapter 7, where the time constant of each tank is shown to be volume per volumetric flow rate, this is V over F, and determine the approximate models using this process at 3 flow rates of stream B given below when each tank volume is 35 cubic meters. So determine approximate models for this process at 3 flow rates of stream B. Stream B and stream A are both inputs. So we have our 3 stirred tank reactors in series. We have an inlet A and we have an inlet B. A is the manipulated variable. D might be considered the load or it might be considered the disturbance, I'm unsure. However, at the end of the pipeline, we have an analyzer indicator. Figure 6.10, for example, 6.4a, 3 tank mixing processes and a process reaction curve for base case. We've been talking about this process reaction curve. We have time and we have valve opening and we have outlet concentration, percent of A. So the 3 process reaction curve experiment was performed for the process at 3 flow rates, all at a base exit concentration of 3% A, and the results at the base case flow are shown in figure 6.10b. The results are summarized in the following table. We have simplified and we have modified. Here we have the modified tau plus theta. For the simplified, we just have theta. And for the, was I saying simplified and modified? I mean simplified and fundamental. So we have proportional gain, we have theta, we have tau, and I'm pretty sure the fundamental is encapsulating theta plus tau, and also the summation of the time constants tau. We have our flow rate in cubic meters per minute, we have our Kp in percentage A percent open, we have our theta in minutes, our tau in minutes, theta plus tau in minutes, and the summation of tau i's in minutes. And that makes sense. That is something that tau is a time constant. It's a time constant, it has time as its unit. The fundamental model demonstrates that the time constants, tau equals V over F, volume over volumetric flow rate, it depends on the flow rate decreasing as the flow increases. That's just simple. I mean, that's high school, that's almost middle school knowledge now. This trend is confirmed in the simplified model as well. Also, the approximate relationship for systems of non-interacting time constants in series, equation 5.41b, that the sum of the dead times plus time constants is unchanged by model simplification, is rather good for this process. The most important characteristics of the process reaction curve method are summarized in table 6.1. The major advantages of the process reaction curve method are its simplicity and short experimental duration, which result in its frequent application for simple control models. Table 6.1 is a summary of the process reaction curve. The input magnitude is large enough to give an output signal to noise ratio greater than 5. The experimental duration, the process should reach steady state, thus the duration is at least theta plus 4 times tau. Theta is the maximum slope of the input variable. Theta is the maximum slope of the initial value. That's correct. Input change, model structure. A nearly perfect step change is required. The model is restricted to first order with dead time, and this model structure is adequate for processes having overdamped monatomic step responses. I'm not sure when that actually showed up. When did that show up? Monatomic? When did that overdamped show up? That overdamped encapsulates zeta, Greek letter zeta, but there was almost like critically damped, underdamped, critically damped step, impulse, step response, something like that. Stuff like that. There was almost like 7 of those. Continuing with the table, the accuracy for unmeasured disturbances. Accuracy can be strongly affected or degraded by significant disturbances. For diagnostic calculations, plot, model versus data, return input to initial value, and then calculations, simple hand and graphical analysis. Yeah, these are supposed to be separate. So like input change and model structure, that's not the same. Like it should be separate. It's not one term. Moving on to section 4. The previously described graphical method had 2 major limitations: a first order with dead time model and a perfect step input. Statistical model identification methods provide a more flexible approach to identification that relax these limits to model structure and experimental design. We've been talking about the 63 and 28% times. So now we're going to section 4, statistical model identification. Is this inferring that we have another method, or like a completely different method, not method 1, 2, 3, but like a new method to use? The previously described graphical method had 2 major limitations: a first order with dead time model and a perfect step input. Statistical model identification methods provide more flexible approaches to identification that relax these limits to model structure and experimental design. In addition, the statistical method uses all data and not just a few points from the response, which should provide better parameter estimates from noisy process data. A simple version of statistical model fitting is presented here to introduce the concept and provide another useful identification method. The same 6-step procedure described in section 6.2 is used with this method, so I'm going to pop up that figure 6.1. The statistical method introduced here involves the following 3 actions. 1. Introduce a perturbation, which means a sequence of perturbations in the input variable. There is no restriction on the stage of the perturbation, but the effect on the output must be large enough to enable a model to be identified. Secondly, collect input and output response data. It is not necessary that the process regain steady state at the end of the experiment. And thirdly, calculate the model parameters as described in the subsequent paragraphs. The statistical method described in this section uses a regression method to fit the experimental data. So we have method 1, method 2, graphical methods. So this is a statistical method, and that's pretty good to note. We're talking about empirical methods here in chapter 6. So empirical methods mean correlating to the data, but there's graphical and there's statistical. So here's what I wrote. So chapter 6, we have graphical, 2 methods, and then we have T, 62%, T, 28%, and then we have our statistical method that we are going to introduce here in 6.4, statistical model identification. Like statistical model identification, like that should just ring a bell for me. Statistical, and the previous chapter was obviously the previous section was obviously separated from section 4. So section 6.3 just titles it the process reaction curve, but really it should just be titled the graphical model identification. So this is 6.3, graphical model identification, and then 6.4, statistical model identification. That was so bad. Identification. Holy crap. Okay. The statistical method described in this section uses a regression method to fit the experimental data, and the closed-form solution method requires an algebraic equation with unknown parameters. Is this like keying me in to say that we have another 2 methods? Blah blah. Plus the transfer function. Let me read it again because I had a question. The statistical method described in this section uses a regression method to fit the experimental data, and the closed-form solution method requires an algebraic equation with unknown parameters. That doesn't make any sense. The statistical method implying one method, or maybe you could have more than one statistical method, but they're just generalizing it. Why do they say it like that? The statistical method described in this section uses a regression model to fit the experimental data, regression, and the closed-form solution method requires an algebraic equation with unknown parameters. So they're saying closed form. Does that imply that this regression method is an open form? Like, why do they say words like that? Thus, the transfer function model must be converted into an algebraic model that relates the current value of the output to past values of the input and output. There are several methods for performing this transformation. My computer just died. Looks like we're done for today. Or it looks like we're done until I go to my meeting while I'm eating my food. So after I eat my food, damn, my mustache is long as hell compared to my beard. You can't see shit. Long ass mustache, boy. What the hell? Okay, so we're gonna pick back up in section. We're gonna pick back up in section 6.4.